Every Java developer, at some point, hears two conflicting statements. Java is a compiled language, and Java is an interpreted language. You probably heard them both. So which one is it? Is it compiled, like C++, or interpreted, like Python? The truth is, it's both. And understanding how Java manages this dual nature is the secret to its incredible performance, its legendary portability, and why it's still a cornerstone of enterprise software after decades. This isn't just academic trivia. It's fundamental to writing efficient, robust Java applications. Today, I want to pull back the curtain on Java's execution model. You are going to master how your Java source code transforms into those mysterious .class files, packed with bytecode instructions. We will then unpack the HotSpot JIT compiler, including its clever tiered compilation strategy and the safety net of deoptimization. I will show you how to use the JavaP tool to inspect bytecode yourself, which is invaluable for diagnosing those tricky performance bottlenecks. Finally, we will contrast the JVM's approach with CPython's, revealing why Java often leaves dynamically typed languages in the dust when it comes to raw execution speed. First, let's talk about the Java Virtual Machine, the JVM. Think of the JVM as a highly specialized CPU, a software-defined processor designed with one purpose: to execute Java bytecode. It abstracts away the underlying hardware completely. When you write Java code, you are not writing for an Intel chip or an ARM chip directly. You are writing for the JVM. This is the core of Java's write once, run anywhere promise. The JVM is the runtime component that takes your compiled .class files, verifies their integrity, and then executes them. Visually, you can imagine it like this. Your Java source code, say a file named myclass.java, goes into the Java compiler. This compiler doesn't produce machine code for your specific operating system and hardware. Instead, it emits a myclass.class file, which contains Java bytecode. This bytecode is a platform-independent instruction set. The JVM then loads this .class file, interprets or compiles the bytecode into native machine instructions for the actual CPU, and executes it. This layered approach is what gives Java its incredible flexibility and performance characteristics. So what exactly is inside one of these .class files? It is a binary container, meticulously structured according to the Java Virtual Machine specification. Every .class file starts with a magic number, the hexadecimal sequence 0x Cafe Babe. This is a quick sanity check for the JVM to confirm it's actually a valid class file. Following that, you will find the minor and major version numbers, indicating which Java version compiled the code, like 61 for Java 17 or 65 for Java 21. This ensures compatibility. An older JVM won't try to run bytecode from a newer Java version it doesn't understand. After the version numbers, the .class file contains the constant pool. This is a crucial table holding all the literal strings, numeric constants like the integer 42, and symbolic references to methods and fields used within the class. Think of it as a dictionary for the bytecode instructions, allowing them to refer to complex data by simple indices. Then come the class's access flags, its own name, its superclass, any interfaces it implements, and finally, the definitions for all its fields, methods, and attributes. It is a complete, self-contained description of a Java class. To see this bytecode in action, you can use the JavaP disassembler. Let's say you have a simple Java class, myMath, with a method that returns the integer 42. If you compile mymath.java and then run javap -c-p mymath.class, you will see the bytecode for that method. For instance, a method like public_int getAnswer empty parentheses curly brace return 42 semicolon curly brace compiles down to just two instructions, bypush 42 and iReturn. Bypush pushes the single byte integer 42 onto the operand stack, and iReturn pops it and returns it as the method's result. This is the low-level language the JVM understands. When you run javap, the output for our getAnswer method would look something like this. Method int getAnswer empty parentheses :0 bypush 42 semicolon 2 iReturn semicolon. The numbers 0 and 2 are bytecode offsets. This direct view into the bytecode is incredibly valuable for diagnosing performance issues. For example, if you have a synchronized block in your Java code, JavaP will show you monitor enter and monitor exit instructions, which are responsible for locking and unlocking the object's intrinsic monitor. It reveals the exact operations the JVM performs. Here is where understanding bytecode becomes critical for performance. A common anti-pattern I've seen junior developers make is concatenating strings in a loop using the plus operator. You might write something like string result equals empty string semicolon for open parenthesis in I equals 0 semicolon, I less than 1000 semicolon, I plus plus close parenthesis curly brace result equals result plus I semicolon curly brace. On the surface, it looks harmless, but if you inspect the bytecode for this loop, you would find repeated, new string builder allocations, and to string empty parentheses calls inside the loop body. Each iteration creates a new string builder, appends to it, and then converts it to a new string object. This generates immense memory pressure and garbage collection overhead. The fix, of course, is to explicitly use a string builder outside the loop. String builder SB equals new string builder empty parentheses semicolon for open parenthesis int I equals 0 semicolon I less than 1000 semicolon I plus plus close parenthesis curly brace s append open parenthesis I close parenthesis semicolon curly brace string result equals s to string empty parentheses semicolon. When you compile and disassemble this corrected code, you will see the new string builder instruction only once before the loop starts. This drastically reduces object allocations and improves performance. Bytecode inspection helps you pinpoint these hidden costs and understand exactly why certain code patterns are considered inefficient. Now that you understand what bytecode is, let's talk about how the JVM actually executes it. The HotSpot JVM, which is the most widely used JVM, doesn't just interpret bytecode line by line forever. That would be too slow. Instead, it starts by interpreting the bytecode, but it is also constantly profiling your running application. It maintains per-method invocation counters and loop backedge counters. These counters track how hot a piece of code is, how frequently a method is called, or how many times a loop iterates. When a method's invocation count or a loop's execution exceeds a certain threshold, typically around 10,000 calls in server mode, the JVM flags that method as hot. It then queues this hot method for compilation by the just-in-time, or JIT, compiler. The JIT compiler takes the bytecode and translates it into highly optimized native machine code for the underlying CPU. This is where Java transitions from being interpreted to being compiled, and it is a dynamic process happening while your application runs. The HotSpot JVM actually has two JIT compilers working in concert: C1, the client compiler, and C2, the server compiler. C1 is designed for speed. It produces machine code quickly, performing basic optimizations like inlining trivial methods and simple register allocation. While it runs, C1 also collects profiling information, such as type profiles and branch probabilities. This data is crucial for the next stage. C1 is about getting code running fast, even if it is not perfectly optimized. C2, the server compiler, is the heavy hitter. It is a highly optimizing compiler that applies aggressive techniques like extensive inlining, escape analysis to determine if objects can be allocated on the stack instead of the heap, lock coarsening, loop unrolling, and vectorization. C2's compilation process is slower than C1's, but the machine code it generates is significantly faster. It is designed for peak performance in long-running server applications where the initial warm-up time is less critical than sustained throughput. Modern HotSpot JVMs use a strategy called tiered compilation to get the best of both worlds: quick warm-up and ultimate peak performance. A method typically progresses through different tiers as it gets hotter. Level 0 is pure interpretation, where the bytecode is executed directly by the interpreter. If the method gets a little warm, it might move to level 1 or 2, where C1 compiles it with increasing levels of profiling. Level 3 is C1 with full profiling, gathering all the data C2 needs. Finally, if a method becomes extremely hot, it graduates to level 4, where C2 compiles it with all its aggressive optimizations. This tiered approach means your application starts quickly with interpreted or lightly optimized code, and then the JVM dynamically identifies and compiles the most performance-critical sections into highly optimized native code. It is a continuous, adaptive process, ensuring your application runs as fast as possible without you having to manually optimize anything. Here is where it gets interesting. The JVM can de-optimize compiled code if an assumption it made during optimization is invalidated. This is a powerful safety mechanism. For example, if the JIT compiler inlined a method call, assuming that a particular virtual method always received an object of a specific class, say my specific class, and then a new, different class, another class, appears at that call site, the original assumption is broken. The optimized native code is no longer valid. In such a scenario, the JVM performs an uncommon trap. It reverts the compiled frame back to an interpreter frame at a safe point and execution resumes in the interpreter. This mechanism enables speculative optimization without sacrificing correctness. The JVM can make aggressive, potentially risky optimizations, knowing it can always fall back to the safe, interpreted version if its assumptions prove wrong. It is a testament to the JVM's sophisticated runtime adaptability. Now, let's contrast this with CPython, the reference implementation for Python. CPython is an interpreter written in C. It reads Python source code or precompiled .pyc bytecode, and executes it on a virtual machine that is much closer to Python's high-level semantics. The JVM, by contrast, was designed from the ground up for static typing. Java bytecode contains explicit type information. The JVM can rely on the fact that a method will always receive a string in a particular slot, for instance. CPython's bytecode, however, is untyped. It must constantly dispatch based on the dynamic type of the operands at runtime. This fundamental difference has profound performance implications. Because Java bytecode has static type information, the JVM can emit specialized machine code that does not need type-checking branches. A get field instruction in Java, for example, becomes a single, direct load from a known offset in memory. In Python, that same operation might involve multiple lookups and checks to determine the actual type and layout of the object at runtime. Furthermore, the JVM's profiling feedback allows the JIT compiler to discover that a virtual method call, which could theoretically go to many different concrete classes, always goes to the same one in practice. It can then devirtualize that call, inlining the method and guarding the inline code with a cheap type check. This eliminates the overhead of a virtual method dispatch. CPython, lacking this static type information and sophisticated JIT, cannot perform such aggressive optimizations. This is a key reason why Java often achieves significantly higher peak performance. Today, you have learned 3 critical things about Java's execution model. First, you now understand that Java source code compiles into platform-independent bytecode, packaged in .class files, which are then executed by the JVM. Second, you have seen how the HotSpot JVM uses sophisticated JIT compilation, including tiered compilation and deoptimization, to dynamically translate bytecode into highly optimized native machine code. And third, you can now articulate why Java's static typing and advanced JIT compiler give it a significant performance edge over dynamically typed languages like Python. Mastering these concepts will not only deepen your understanding of Java, but also equip you to diagnose and solve real-world performance problems. Next time, we will explore how Java is evolving beyond the JVM with Beyond the JVM, Graal VM, and Native Image, which takes Java's performance to an entirely new level.